Alright, so we're going to talk about sequences just in general for this section, and then we'll later talk about two specific types of sequences. But a sequence is a function where the domain is the natural numbers. So I could write, say, f of x equals x squared plus 1. I could write a sub n equals n squared plus 1. The difference between these two is this n generally implies that you start with 1 and that your domain is just this. Sometimes it starts with 0. Typically it starts with 1. I could also just list out random numbers and that can be a sequence as well. So a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. That's a finite sequence. We typically look at infinite sequences. Sometimes we just list them. Sometimes they're defined like a function. So a sub n, say, equals n squared plus 1. Then when you go to list out the sequence, you plug in 1 and you get 2. You plug in 2 and you get 5. You plug in 3 and you get 10. You plug in 4 and you get 17, and so forth. Also, if I listed these for you, you might be able to guess n squared plus 1. There is a way to recognize if it's a squared or a cubic or a quartic and so forth, having to do with the differences. I'll show you very quickly, I guess. Let me move this down. Well, actually, let me just start relisting it. If it had been 1, 4, 9, 16, 25, and so forth, I assume you would have recognized it right away. So let's say that it's not. Let's say that it's adding 1 like that. So what you do is you come up with a list of the differences between them. So 3, 5, 7, 9, 11. Difference between these two, 2, 2, 2, 2. If at some point it begins to be all the same number like this was, then if that number is a factorial, which we will deal with shortly anyway, then, okay, so in this case, let me back up somewhat. N factorial is n times n minus 1 times n minus 2 down to 2 times 1. 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, and so forth. If the repeating number ends up to be a factorial, then that's the power of the thing. So because this is 2, then you would say this has to do with x squared. If that all been 6, it would have had to do with x cubed and so forth. I don't expect you to be asked to kind of sort that out, but just for your own personal edification, there it is. So that's when you have a sequence defined just like a function. So a sub n is, say, 2n plus 3. Then you would say a sub 1 is 5, a sub 2 is 7, a sub 3 is 9, and so forth. On the other hand, you can have sequences defined in terms of previous terms. So if I said, for example, a sub 1 is 3, and a sub n is 2 times a sub n minus 1 plus 1 for n greater than 1. Then a sub 1 is given, it's 3, so you just say 3. For a sub 2, let me write this out one time. That's 2 times a sub 2 minus 1 plus 1 is 2 times a sub 1 plus 1. So it's 2 times this one, 6, add 1. The next one will do 2 times this one and add 1. Then 2 times that one and add 1, and so forth. The previous way to define where it just looks like a function is called explicitly defined sequences. This is called recursively defined sequences because each time you have to know the guy before to get the next one. Recursively defined means you're building from one to the other. Okay, so if we look at this one, it's explicitly defined. It tells you just as though it was a function, and we want to find the first 4 terms of the sequence. So a sub n is minus 5n cubed plus 9. A sub 1 is minus 5 times 1 cubed plus 9 is 4. A sub 2 is minus 5 times 2 cubed plus 9. That's minus 40 plus 9. A sub 3 is minus 5 times 3 cubed plus 9 that's 27, so minus 135 plus 9, negative 126. A sub 4 is minus 5 times 4 cubed plus 9. 4 cubed is 64, so minus 320 plus 9 is minus 311, and that's the first 4 terms. Then the next one, the nth term is given this way. Anytime you see minus 1 to a power like this, let me zoom in a little, it's going to end up alternating sign. It'll be negative 1 to an odd power is negative, and then negative 1 when it's an even power is positive. So we end up with negative and positive. If I put in an odd number for n, then n plus 5 is even. So the odd numbered terms end up positive in this case because of that plus 5. If I put in an even number and then add 5, now it's an odd number. So the even numbered terms end up negative in this case. Okay, so this is not a sequence. This is going to be referenced on the next one. We want to match the function with the graph. 3 over x is just a stretched 1 over x, right? So it should look like a here. It's continuous because it's a function. This is just normal like you've dealt with all along. When I instead, though, say a sub n is 2 over n, it's still going to look like this over here, but now it needs to be dotted like this and only be defined over here because it's only defined on 1, 2, 3, 4, 5. It's not defined on the negatives. It's not defined on the halves. So it's just this C. Okay, this one is defined recursively. We want the first 5 terms. The first one is given. So minus 2, that's the first one. Then a sub 2 is 4 times a sub 2 minus 1 plus 8. So 4 times negative 2 is negative 8, plus 8 is 0. The next one we do 4 times 0 plus 8, 4 times 8 plus 8, 4 times 40 plus 8, like that. Oftentimes you're just given a sub 1. You have to be outright given however many you need. If you've heard of a Fibonacci sequence, Fibonacci sequences, the Fibonacci sequence, you can have any Fibonacci sequence, you just define the first 2, but the typically known Fibonacci sequence begins 1, 1, and then you always add the 2 before. So 2, and then 1 plus 2 is 3, and then 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so forth. But the way you define it, because you needed 2, because you're always adding the 2 before, so you have to have 2 to start with, a sub 1 is 1, and a sub 2 is 1, and then a sub n is the 1, 2 before, plus the 1, 1 before. And when you do this in a sub n minus something, that means step back that many times. So I want to step back twice and add that to stepping back once. So stepping backward is subtracting 1. So this is how you define a Fibonacci sequence, and these two numbers could have been anything you wanted, and it would still be a Fibonacci sequence, just not the kind of most famous Fibonacci sequence. Okay? So factorial, I just mentioned before. So if we want to calculate that, this, you could of course put it into your calculator. These are kind of fun anyway. So I have 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. And then on the bottom I have the 6, 5, 4, 3, 2, 1. So these all cancel, and I just get 9 times 8 times 7. And that's that. To put it in your calculator, that's in probability. So you would go 9 math probability, and there's the exclamation point right there on 4, divided by 6 math probability exclamation point. Okay, so this time we just want to find d sub 4. So that means I plug in 4 everywhere I see an n, it's just like a function. So 4 plus 4 factorial over 4 to the 4, to the 4. Okay, so one of these can just cancel. The 8 and the 2 have 2 4s in them. So let's see, 6 and 4, that's 3, 2. So we have 7 times 3 times 5 times 3 over 2. And there's our simplified fraction. Okay, to find the sum here, this means summation. This tells you where to start. Oops, it's usually I. It's m in this case. This tells you start with m equals 3, and then you just would go 3, 4, and then stop at 5. So if this said 3 to 10, you'd go 3, then 4, then 5, then 6, then 7, then 8, then 9, and then 10. And you add them. So this is minus 1 to the 3 minus 1 times 6 times 3 plus minus 1 to the 4 minus 1 times 6 times 4 plus minus 1 to the 5 minus 1 times 6 times 5 equals. So this makes it positive because that's squared, so 18. That makes it minus because 4 minus 1 is odd, so minus 24. And then the last one will be plus because it's to the 4th, 30, which equals 24. Okay, so when you look at this, this is an example. The top seems to be counting up 4, 5, 6, 7, 8. The bottom appears to be multiplying by 5. But this doesn't count up starting at 1. So on the bottom, it would seem that it's 5 times n. For a sub 1, it's 5, a sub 2, it's 10. On the top, though, it's 3 more than n every time, so that would be what we call the apparent nth term. You can't know for sure. Somebody could start out a sequence in a pattern and then suddenly change their mind, but the apparent nth term is the one that it seems to be indicated by these ellipses. So 3, 9, 27, 81, 243, it appears that we're always multiplying by 3. So if we're always multiplying by 3 from the previous term, then on the first term, I've just multiplied by 3. I've just got 3. The next one, I've got 2 3's. The next one, I've had 3 3's. I get a new 3 each time. So the apparent nth term is 3 to the n. Okay, so this one we want to kind of break this apart. I've got I equals 1 to the is given to me. I have 1, 2, 3, 4 things, so I need 1, 2, 3, 4 things. So that would be a 4 right there. Each time I'm just adding 8. It does not depend on I at all, so I would just write 8. This one's slightly more interesting. So I have 19, 18 pieces because I don't have just a D. So I start with 2 and land on 19. So I have 18 things. 1 to 18 would make 18 things. And it's D to the something. The something is counting up 2, 3, 4, blah, 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 but it starts at 1 bigger than 1. So I plus 1. All right, these are things which are known. If you add up the first n terms, well, we'll get to that actually on arithmetic sequences. So we're going to be told what I from 1 to 50 of I squared is and what I from 1 to 50 of 1275 is, of I is, and just use it. So here's the thing. If you have the sum I equal A to B of K times something, say B to the B sub n, shouldn't use B, M sub n, you can factor out the K. If it's just a number of times that you can factor it out. Also, if you have I equals, we'll say M to n, A sub n plus or minus B sub n, you can split them because addition is commutative. Multiplication and division are not. So you can't do that. Well, multiplication's commutative, but you can't split it up like that. But addition you can, because this also means addition and this does not also mean multiplication. So you can just split it like that. So in particular, in this case, this sum equals sum I equals 1 to 50 of 4I squared minus I equals 1 to 50 I, and then I can take out the 4, and then I've been given these. So this would be 4 times 42925 minus 1275. And then you just put that into your calculator, whatever that is. It's just that. All right, expenses for a company for 1 year are $45,000. Every year after that, they increase their expenses by $1,400 plus 3% of the cost of the prior year. A sub 1 is therefore 45,000, and we want to know a recursive formula that gets the rest of the terms. So happily, we're not trying to figure out how to write this just as a function, but we know what a sub 1 is. And what we know is a sub n takes the year before and it adds to it 1,400, just dollars, plus 3% of the prior year. The prior year step back a year. So we could write that as 1.03 a sub n minus 1 plus 1,400. That's a little cleaner. That's just because I have one a sub n minus 1 and then another 0.03 a sub n minus 1. So that's collecting like terms there. We know that I is the square root of -1, so we want to find the first 7 terms of the sequence defined by a sub n equals I to the n. Okay, so the first one, a sub 1, is I to the 1, and then it's going to be I to the 2, I to the 3, I to the 4, I to the 5, I to the 6, I to the 7. This is I squared is -1, multiply by I again, you get -I, multiply by I again, and you get -I squared, so -1 times -1, and then you multiply that times I, you get I, times I again is -1, times I again is -I. That pattern continues off to infinity. Okay, so these are about using the graphing utility to find the sum. So if you go into your calculator and you go to list, then you go to math, and there's sum right there. It's number 5. So I want a sum. And then go back to list, ops, and go to sequence. Now mine pulls it like this. If yours doesn't, you insert each of these things separated by a comma. So you would put the function, comma, the variable you're using, comma. So you could choose to use any alpha letter that you prefer, or you can always use X, it doesn't matter. And then you just put comma, the variable, comma, where do I begin, comma, where do I end, and then the step is always 1. It's always going to be 1. That will show up. After I enter this, it'll show up how you would have had to type it in if you don't have it come out like this. So I'm going to want the -1 to the power of m minus 1. So I'm going to use the variable x minus 1, but you can use m if you want to. And then times 5m, which I'm again going to use x. Okay, x, we want to start at 3. We want to end at 5. Okay, so here's what it looks like if you have to type it in. So the sum is still over there. And then sequence. and then you put in the expression, comma, the variable, comma, the beginning, comma, the end, comma, 1, always. And this is 20. So we would have just put in 3, which would have given us a positive 1 times 15. And then we would have put in 4. So positive 1 times 15, and then minus 20 plus 25, which is where the 20 comes from. Okay, so now that you've seen how to put it in the calculator, this series will eventually go to natural log of 1.5 as we let n get larger and larger and larger. We want to look at when n is 5 and when n is 40 and see which one's kind of a better guess. Typically, if you have something as the limit, it will get closer and closer. Sometimes it waits a while to do that, but in this case, I think it will get closer and closer. So first, let's see, what is natural log of 1.5? 0.4054651081, and there will be infinitely many things after that. So let's go into list, math, hit sum, and then back to list, and this time ops, and hit sequence, and then -1 to the x minus 1 times 0.5 to the x divided by x, and then my variable I've chosen is x. I start with 1, I end at 5, and I get 0.40729, so not terribly far. Now I'm going to go back up, copy that down, but this time I'm going to go instead to 40. And I get 0.4054651081. At this point, you can't even tell, the calculator can't even tell the difference between them, really. Just out of curiosity. Yeah, it can't even tell the difference between them. So it's pretty far out before it's different. So 40, you're already starting to get there. Okay, so that wraps this up, and that's that.